welcome to my presentation. I know Christoph already for more than 20 years since my time in Graz. And I'm going to present you my work on the code-modulated visual evoked potentials. We had already several montages today, and it would be really interesting to see how it is working and to show you what are the typical speeds of this device. Here's the overview of my presentation. I will start with a brief history of biomedical recordings to show you also, because many people thinking that BCI technology started with the publication of Jonathan Wolpaw from 2002, which is also here. Actually, SSVEP and so on started much earlier. Therefore, I will really spend several slides for the history of biomedical recordings, then about the EEG, especially very, very typical error, what I see every time if I review papers. All people are using 10-20 system, which is actually particularly not true. Then I will explain what are the typical information transfer rates available with the BCI, and I will end this presentation with a short overview how we can actually speed up this. And to answer this provocative question, what is the best VEP BCI paradigm? Of course, this is provocative, and we will be able to talk about this. Okay, I will start with a galvanometer, which is electromechanical measuring instrument for electric current, was invented by Luigi Galvani. And so this device was later called after him in the year 1836. And researcher Galvani found that applying electrical current to the spinal cord of dead frog could generate muscle contraction in its limbs. At that time, he was waiting for the rain, and if he is able to get some feeling, then this electricity was provided actually in the totally hazardous way, but it was possible for the first time to measure this. So later on, already in the year 1875, and this paper was cited by Hans Berger, which will be shown on the next slide, it was possible for the first time to measure the electrical activities from the gray matter, from the rabbits and monkeys. So you can see already in this year it was possible to measure this. Here's just schematic representation. Of course, they were using different machines for this, but showing that we were able to measure electrical activities, and especially if the eyes of the rabbits were illuminated with a bright light, it was possible to measure electrical activities in their brains. For us, it is the most important to measure the electrical activities in humans, and it was discovered by Hans Berger in the year 1924. And in the original wording, it was electroencephalogram, which was later used to the abbreviation EEG, electroencephalogram, how we are using this also in the future. At this time, it was also much longer publication times, because all the manuscripts were sent by the normal snail mail. And so one publication took easily several years at that time. So here in the lab, on the left side, you can see here at the bottom our locations. It is from the O1 electrode, and it is important. I will show on the next slides more details, but it is just for the one electrode signal. And the alpha waves, which are sometimes also called Berger waves, which are in the range between 8 and 13. You can see the 8 is a little bit in bold. I will stress out this later. Beta waves also in the 13 between 30 hertz. But what is possible and clear, and what was also Berger discovery, if the person is closing his eyes or her eyes, then we have the strong oscillation around 10 hertz. And if the eyes are open, then we have the normal EEG, which, as it was shown already many times. So this can be measured non-invasively, and this is additional added value, because previously, of course, in animals, it was only invasive technique available at that time. So in the other publication, you can see the different EEG waves, which are delta, theta, alpha, beta, and gamma. And what is important to see here, that the values here are 8, 8, 13, and these values we will find in different sources that are slightly different. We engineers prefer to have everything in the distance. Still 8, it is one band, from 8 is another band. In reality, it's not like this. You will find several sources where Alpha is between 7 till 13, and so on. So they are sometimes not overlapping. This is correct in this form because we are all human individuals, and we have another factor, which is age. So many medical doctors will be defining which frequency belongs to which frequency band. It is dependent very much also on the age of the subject. Therefore, try not to be fooled. Sometimes we will see different bands for different waves. And here's another option. What we learned very often, as I already stated, 1020 system. The 1020 system was introduced by Jasper in the year 1958, and it has altogether, if you are taking the electrodes in the circle, altogether 19 electrodes. Very, very easy. If you're using, we are working with the visual evoked potentials, then we see that the OZ electrode is used, so you cannot see it here. It would be here between O1 and O2 in the middle, but it's not there. That means if you are stating that your system is 1020 and you're writing OZ, then something is not correct. And this is indeed not correct because usually in the BCI research, we're using 1010 system, which is here, and you have up to 8 electrode positions, sometimes 74. There are also ambiguities in different sources, but OZ electrode is there, and many people are trying to use this. Later on, nowadays, you can also use 10-5 systems. By the way, 10 and 5 are degrees, and they are showing you what is the angular distance between the electrode positions. In this case, you can go up to 345 position. Therefore, you will be on very, very sure side if you'll be using for the VEP recordings 1010 system as abbreviation. In this case, you will have most of the electrode positions. And usually, if we are using the g.tec amplifiers, we have to use one additional reference electrode. And the reference electrode shown in blue is the signal which will be deducted from the other. Therefore, it is not so much important where your ground electrode is located. You will be always deducting the value of the reference electrode. So this was just very, very important part. Therefore, if you will be publishing from today, please try to use 1010 as abbreviation. You will be on the sure side. Okay, once again, that it's not started in the year 2002. Already in 35, it was possible to measure action potentials in the brain through the intact skull. You can see here that recorded evoked potentials in humans. Evoked means if you have some visual stimulus outside, then you will be able, as a response to this, some changes in the EEG. It was also possible to measure in newborn children and in very, very small infants. You can see here that already 26 months later, in the 60s, we had no ethical committees and so on. So all researchers were always treating the new Earth baby. If they are interested to find something, there is no big deal. And it was possible to find that already with 2 months, it is possible to see SSVEP responses there. The rise of SSVEP started also from the Jasper, the same person who published the paper about the 1020 system. And you can see here very, very old electronics. I'm basically an electronics engineer. Therefore, I provided for you some small video how it is working. Namely, if you are starting this with this one, then you will be able to have this flickering. I hope the video will be working. Okay, probably this is because of Zoom. You will get here different frequencies. Important is that on top here, we are in the range of approximately 2 Hertz, which is not correctly in line with SSVEP. SSVEP response should be in the range between 1, actually between 6 and 90 Hertz. Many people at that time used for the stimulation so-called checkerboard patterns with alternating blade and white patterns, as is shown here. They were commonly used in diagnostic optic nerve and visual pathways disorders. Nowadays, it is also used in the neurosurgery in order to find which part of the brain is disconnected in order to perform surgery to remove this part of the brain. This is how it is working. It is in the year 1972. Then here, as I already mentioned about the children in the age of 2, 3, and 4 months, and they were able to find VEP responses there. And then in the 90s, we started a very, very big development of different solutions. And probably for one of the quizzes, what was the first SSVEP BCI or cVEP BCI? The correct answer, it was the code-modulated one. And here's the paper by Sata. And he created one invasive system with just only one individual using this. And this ALS patient was able to use this system and was able to communicate with the speeds up to 12 words per minute. This is the diagram from the year 1984, and it is explaining basically more or less the same what we are showing in the BCI system nowadays, but very, very old and ancient hardware at this moment. Here you can see also 32 pages of key functions, and this is how it is working. Important is that it was already in the last century, and somehow it was not really followed later. It is really interesting system. Of course, it was invasive one, but it was really working well because 10, 12 words per minute is the speed which is also very, very normal in the modern times for the non-invasive BCIs. So, and then in the year 2002, Volpov defined BCI in his review as a system that enables its user to interact with his or her environment without the use of peripheral nerves and muscles. That means you should get the signal directly from the brain. But according to my historical overview, you can imagine that even with the paper from Sata, it is already working. It was working as a BCI, and our pioneering paper was by Vidal in the 1970s, and this is one of the papers which we are using for this. So don't be fooled, BCI was already prepared much earlier. And so I'm coming to the main topic of my presentation. What is the code-modulated visual evoked potentials? For this, I'm starting with the review of Bin et al. From 2009. They divide all the visual evoked potentials into three categories. First, TVEP, time modulated. And if you will see here approximately 300 milliseconds, you should know what is the other name for this. It was presented today. We are talking about the P300 BCI. So we are not covering this in details. The other one is the frequency coded steady state visual evoked potentials. If we have our stimulation in different frequencies, and these frequencies are showing or represented as the peaks after the fast Fourier transform, so you can easily detect them. And the last one is about the cVEP code modulated. In this case, you have specific modulation like this. I'm presenting this also in my classes for the students, and my idea was how to explain this in people that they really see and remember this in a very, very nice way. So for these, I presented several things. Once again, let us compare them and see the differences. For the steady state visual potentials, we have different frequencies, 14 Hertz, 20 Hertz, and so on. In case of cVEP on the right side, responses produced by specific code patterns as stimuli, and these code patterns usually utilize M sequences. Here is a short video. I hope it will be working. This is a constant one for the SSVEP. And this was code modulated sequence. And then I thought what can be used for us electrical engineers in order to see in more details about this. And I created here this slide about the amplitude modulation versus frequency modulation. In case of the AM modulation, which is now not used so often, but was used as a radio frequency modulation at the beginning, you have your carrier frequency with the same frequency, and actually the data is transmitted as an envelope. As an envelope on this, that means much lower frequency here in the amplitude, and this is your data. That means your audio data is transmitted here. And then later we used frequency modulated, and in this case it is shown here. That means also the data is shown in the frequency, and if you used to hear to the audio from the AM radio or FM radio, you can remember that the FM was much better signal quality. And therefore, I would say the analogy, of course, it's totally different thing, but the analogy is for the SSVEP, we are transmitting the data exactly in this frequency, which can be 10, 12, 14, and so on hertz. In case of the cVEP, we can use the same carrier, that means the same M sequency, and our data will be transmitted in the phase. Phase shift will be actually our signal, which is used here. Of course, we did this also on their own data, again from the channel 01. If you have the person who was gazing at the SSVEP stimuli flickering with 10 Hertz, then you can clearly see the peak here at the FFT at this frequency. This will be also a little bit a problem if you will be using SSVEP BCI, because if some people will be closing their eyes, that according to the Bergers or the alpha waves, you will have some activity also in 10 Hertz, which can be misclassified as a target. Therefore, SSVEP has several drawbacks, and the typical solution used in the last years was to avoid this alpha range. So you should stop, you should not use the frequencies between 9 and 11 Hertz, because of this problem. For the cVEP, we try to do the same. In this case, you can see that the EEG data already not so clear as previously, but if you will be averaging over many trials, you will be able to create your templates as well. Therefore, it is working well, and I hope to be able to show you this later. Once again, from the Sutter paper, he described this, how to do this. There are several ways how you can create the IM sequence, and it is a linear feedback shift register, and you should use the XOR, exclusive OR logic, in order to calculate this, but much easier to understand this on the next slide, not on this one. What are the properties of M sequences? They are pseudo-random binary sequences created by linear feedback shift registers or on the basis of flip-flops. They are autocorrelating, and they are spectrally flat with a 0 Hertz peak. Here, example with the flip-flops. A shift register is a digital circuit using a cascade of flip-flops. Output of the flip-flop is connected to the input of the next one. And here is in the form of linear feedback shift registers. M sequences were used already in many other things, especially in the data transmission, because they are really providing feedback in form without a lot of noise. That means the chance that the noise will be having the same signal as the M sequence is very low. The relationship between the tapes can be expressed by polynomial infinite field arithmetic with a modulo of P. And here's one polynomial to generate M sequence, one of the used in our research. Please pay attention that they are always having +1 at the end. And here you have several ones in this case. And here is one implementation in the flip-flops. And the video is showing here an example of 31 bits. The same can be created for 33 bits. And important is just to mention that why they are called maximum length sequences. If you will be creating the signal which is not belonging to this one, then your sequence will be shorter than 63 bits or 31 bits. It's always 2 to the power of P, what was produced. In this case, if we are talking about these different values, you can only have several M sequences for every P. Here is one MATLAB code, how you can do this also with MATLAB. And you should only select here the number of flip-flops. This is your power. Initial state, which is your initial state, which is there. And then the tap points, which is our polynomial. And then with this, you can return this sequence. If somebody is accessing this over the Zoom, then you can create a screenshot and try to use this. Important information of these M sequences is this: they are using, they have very nice autocorrelation properties. That means if you have the same sequence and you will shift this in time, which is information of your shift information in the phase, then you will have very nice signals here, and which is also shown here. In theory, it will be a flat line except the 0 with the maximum value here. And here's the explanation how we are using this for our BCI. Now we should go from the flickering to our BCI. When gazing at the flickering light source, cVEPs are elicited in the visual cortex, which can be measured in EEG. M sequences different time lags can be used for stimulus modulation. You can see here, it is not very, very obvious that they are the same sequences, but just shifted in time. And this is shown here. We have here the same sequence of 63 bits, and you can see here by red that this green is coming to this. So that means every new target will be the previous one shifted by some value. Please pay attention that this time shift is also important because you have your jitter. If you are transmitting, for example, the data over live streaming layer and so on, then you will having some very, very different delay here. So you cannot go to the shift of just one frame or two. The minimum value, depending also on your vertical refresh rate of the used monitor, should be different value here. And so if you will be seeing how many of the sequences are available, you can see here that we have only limited number of M sequences. For example, only 6 for each P base of 5 or 6, which is shown here on the right side. As I mentioned, always this +1, otherwise it's not working. To increase the number of BCI targets, we need smaller bit shift, but smaller bit shift reduces accuracy as already introduced. Some other way how we can overcome this by use of other gold sequences which are similar and have similar properties as M sequences, but I will be not covering this here today. And just the idea is slightly different. Some people would say, why we are using time shifts? If we are shifting of only 2 bits, it will be problematic. We will be using, we have here different 6 sequences, for example, for 5 and 6 bases. Why not to use different one? And in this case, the answer is you should never use 2 different ones because it will be shown in the next slide. You will have the problem that your autocorrelation property will not be given. And this is explained also here. Here you have all possible sequences for the for our 636 bits long M sequences, which are shown here. And by creating here, you will find the following for all M sequences with the P greater than 1. For 1, you will have only 3-bit sequence 110, therefore it's slightly not working. But for all other ones, you have always 2 groups, like here, red and red, yellow and yellow, green and green. That means, of course, there is no information in the order. You can go and shift from the left to the right and from the right to the left. It means if you're having here the red one, it is 5 zeros, 1, 4 zeros, exactly the same, 5 zeros, 1, 4 zeros, and they are going and descend. It means you have always 2 mirrored, so-called mirrored sequences, which are, as I already mentioned, in pairs. And this is also the problem. If you will be correlating different M sequences here, then you will see cross-correlation of different M sequences. You have 6 of them, and you can see here that it will be not 0 anymore. That's the one sequence. If you will be using another one, you will have some higher correlation, even if it is not expected. Therefore, it is not the way because somebody would have the idea, okay, I will use 1, 2nd, 3rd M sequences. No, it's not the good idea. You should stick to the phase shift. Okay, I hope after this introduction you can understand how the M sequences and cVEP are working. And I'm showing you, I still have some minutes, I hope, several applications. First is from our friends, cooperating partners from the Netherlands, and Jordi is also in the room. This is the cVEP at Radboud University. For the cVEP, it is usually necessary to have some training, which is shown here. And during the training, you can averaging the responses and to create the class templates. If you are interested in this information, you can see here at the bottom the corresponding paper. And for the BCI, we are talking about the BCI only if it is online BCI. And what you can see on the top of the screen, the spell text and also some potential auto-completion versions. Okay, the complete word neurotechnology was spelled. The next one is the cVEP group from Spain, from Valladolid. And for them, I only got this video if I promise to make some small advert for the Medusa BCI, which is a free of charge tool which you can download and use. Here we can directly see the online spelling, but it was, of course, also used with the training. Little bit advertisement for tomorrow BCI session. We have one publication about training free cVEP. I'm interested to hear about this. Then in the year 2019, we published at the Rhine Valley University this video with cVEP in order to spell the word BCI. This is the third application. In all three of them, we use different hardware. I don't know if you paid attention that all the EEG amplifiers were slightly different here. And the last video for today is something what we submitted for the BCI award, g.tec BCI award in the year 2020. Unfortunately, we are not selected, but you can see here. This is lowered down in speed. Speed is 50%. Noise is absolutely not a problem here. Now you can see some real-time speed. And the very, very logical question is why we are so much faster? Are our algorithms so much better and different from the other groups? The answer is not. What we have created here in this video, we used the Microsoft Visual Studio, Visual C++ in order to create our graphical user interface. So we don't have this jitter, which can be several milliseconds if you're transmitting your data over a lab streaming layer and so on. So this will be giving you some additional speed. So I would really encourage you, if you will be going in order to get some higher speeds here, you should go and use and create your custom-made software. And as I mentioned, I'm at the last slide of my presentation. Here is the question, is there a best BCI paradigm published in the Journal of Neural Engineering, one of our special journals for publishing BCI research? And Dong in the year 2025 provided this nice overview here of different BCIs based on visual evoked potentials, where you can see the target amount. And of course, if you're going with a higher number of targets, it means your N is higher, you can transmit more data. But you can see here that also with other one, which is here in this case, SSVEP, you are able to get for 40 targets over 200 bits per minute. So if you will be asking myself, what is better, SSVEP or cVEP, I would absolutely clearly state cVEP because you have better signal to noise ratio, and so you are working faster and better. But you can see from this overview that it is also possible to be able to get higher response rates with this. For comparison, TVP or P300 are not so good. You can see here it is in the orange one, so you rarely have something more than 15 bits per minute. So this is really nice overview from this point of view. Thank you very much for your attention.
Are there any questions for Ivan? Let me check there.
Okay.
So why is it so tricky to do cVEPs? What's important when you're implementing it?
As I already mentioned, all the timings should be perfectly valid. So we are using here in this case not the normal monitors displays with 60 Hz vertical refresh rate. We are going into 360 Hz monitors because all these small milliseconds, they are really important here. It is really tricky because you are actually getting the information only in phase, and it is totally different from the SSVEP, and it is not easily solvable in this way.